we're asked to find all vertical and horizontal asymptotes and pertaining limits for, and I'm making up a function, f of x is x minus 1 over x squared minus 3x plus 2. Very important type of problem. We need this for chapter 3 and 4. So we are given a rational function. It's a rational function because it's a polynomial over polynomial. And we're asked to find if it has vertical and horizontal asymptotes. What do you recommend we should do first? What would be our first thought here? What would you say?
Plug in 0. Oh, never mind.
This is not a limit. We are going to determine some limits, but not yet.
Actor.
Thank you. Yes. 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 Absolutely. Thank you. Can anyone help?
X minus 1, x minus 2.
Excellent. Thank you very much. Very good. Do not attempt to simplify anything. We have to state restrictions first. Where is this function undefined?
At 1.
Of course. Now I can simplify. 1 and 1. So the simplified form is 1 over x minus 2. So I have to investigate what happens here. So this whole thing right now deals with vertical asymptotes. Okay? But I have to investigate. Notice one thing. This factor disappeared. So this factor is gone. If a factor is gone, it's not in the simplified form. 1, so I'm going to call point A 1, comma, we'll see in a minute. Okay, this will be a whole, not a VA. Okay, so in order to find that whole, I have to plug in 1 in the simplified form, not here. Here I get 0 over 0. I'm not going to get anything. So in the simplified form, I know that this is not a vertical asymptote, but a whole. To determine the y-coordinate of the whole, so I know where to graph it, I have to plug in 1 here. Can anyone give us the answer when we plug in 1?
-1.
That's it. So this is done. It will not be a vertical, it will not be a horizontal, of course. So I already determined the limit. The limit from the left is -1. The limit from the right is -1, clearly. And it is a whole, because the function value there does not exist. It's undefined. So now all I have to investigate is x equals 2. Okay. I know that x equals 2 is a vertical asymptote. There is no discussion there. I know x equals 2 is a VA. But the problem is asking me to find the pertaining limits. So when I get the chance to graph this function, this will be x equals 2. But I need to know if on this side it goes to infinity or negative infinity, and if on this side it goes to infinity or negative infinity. I don't know. That's why I have the concept of the limit. So I will say limit as x approaches 2 from the left, from the simplified form, of course, and the limit as x approaches 2 from the right of the simplified form. And this will conclude the discussion on the vertical asymptote. So that is done. So can anyone give us the limits? We just did this a few minutes ago by chance. What does this equal to? What does this equal to?
From the right is positive. The left is negative.
That's it. So the conclusion is done. We're not asked to, thank you so much. We're not asked to find the limits from either side, right? There will be D and E. All we're asked to find is the vertical asymptote and the limits left and right. This is extremely important for next step in the next chapter. Okay, now I have not analyzed horizontal asymptote. But for horizontal asymptote, I have to determine the limit as x approaches infinity and the limit as x approaches negative infinity of the simplified form. Can anyone give us the answer here?
Zero
Thank you very much.
and zero.
Of course, a number over huge. A number over huge when, of course, this is the case. So then I say y equals 0 is a horizontal asymptote. Done. I don't need to do anything else. Okay. Any questions for me? Any questions? So we know now how to determine horizontal and vertical asymptotes. And the last topic of this chapter deals with, so this is the 2.7 and 2.8 together. We're going to talk about the derivative function. Okay. We know two concepts so far. Big concepts. One concept is the concept of the limit. And the second concept is the difference quotient. And we know what it is. It's f of x plus h minus f of x divided by h. When we put these two together, the limit of this, limit, of course, when h approaches 0, from f of x plus h minus f of x divided by h, this is a function. The notation is f prime of x. Another notation is dy over dx, the derivative of y, because this is the same with y prime. So the derivative of y with respect to x, it's a function, and this is very important, what I'm going to write next, that gives the rate, the instantaneous rate of change of function f of x at any point where, and this is what I need to talk about next, that's my next step, and then I'll come back to the definition, that it's a function that gives the instantaneous rate of change of f of x at any point where, and this is a fancy word, the function is differentiable. This is a fancy word. I did not explain what that means yet. So I'm going to explain what this means, and then I'll come back to the definition. Okay. It is easier to talk about when a function is not differentiable. Not differentiable. When is a function not differentiable? Here's one. Not continuous. So if a function is not continuous, cannot be differentiable. It is differentiable here. In other words, at this point it has, let me use a different color. It's differentiable at this point because it has a unique tangent. It's differentiable at this point because it has a unique tangent. So if this is a function, the distance function, and I have the distance function, and you ask me at time t equals blah, 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 what was your speed? I will tell you, if this is the distance function, I will differentiate it and plug in this value and tell you what was my instantaneous rate of change. The function is differentiable here because it has a unique tangent. There is only one rate of change here. It's given by the slope of this line. However, at this point, the function has two tangents. A tangent here that is whatever, and a tangent here that is whatever. Because it has two tangents, it's not differentiable. It has to have a unique tangent. I can tell you that at that particular instant, I was driving at either 40 miles an hour or 55 miles an hour. No, that's not possible. I have to tell you exactly one number. If I have only one number for the rate of change, the function is differentiable there. If I have two numbers, you'll say, you can give me a number. Here's another. Okay, in any situation that is not continuous. So in this case, see, the function is continuous. But even if it's continuous, it has two tangents. It has a negative tangent on this side and the positive tangent on this side. Because I cannot give you one tangent or one rate of change, the function is not differentiable. Although continuous. We call this a cusp, like between two teeth. Another possibility is a corner. Corner. If the function has a corner, it has a negative tangent here and a positive tangent here. You cannot say this. That's not possible. You cannot say this. That's not tangent. This is tangent. Here it's not. So the tangent is at the function. So cusp or corner, not differentiable, because there are two tangents. And there is one more. Of course, you can put a coordinate system. And there is one more, something like this. It's a very simple example is the cube root of x. The cube root of x looks like this. At that point, right here at 0 for this, it has a vertical tangent. At this point, right, the vertical tangent means the function is not differentiable. Okay, it's differentiable here, it has a unique tangent. It's differentiable here, it has a unique tangent, one rate of change. Is differentiable here, but not here, because you cannot give me a number. Give me the slope of this line. It's undefined. So if the tangent is vertical, we cannot have a derivative or a rate of change because the slope of this line does not exist. The slope of this line exists. I don't know, it's 3. The slope of this line exists. I don't know, it's 4 because it's steeper than this. But the slope here does not exist. You cannot give me a slope here. So not continuous of any type. It can be infinity, whatever, not continuous. It can have a gap, doesn't matter. It's not continuous. If it's not continuous, it does not have a unique tangent at that point. You cannot give me the rate of change here. Function doesn't even exist. So it cannot have a derivative, or we cannot find a rate of change here if the function doesn't even exist there. So not continuous, something like this with two tangents or a vertical tangent. Okay. So coming back to all this. So let's look at a simple situation in which we pick a simple function. Can anyone give us a simple quadratic function?
X squared plus